And the thing about confidence intervals is that sometimes they are a little bit more complex. So I'm going to read you a little bit of what they are out of this book. It's a statistics book. That's not the one that's used to create this class, but it'll maybe backfill a couple of things. So it talks about, there's an example that's going to talk about. It's not the best example that they give of a life situation, but I want you guys to hear this, and then you have to suffer through my reading skills. So this is titled confidence intervals. Okay, a distribution can't provide us with generalized data about populations, but it doesn't tell us as much as any individuals in the population. Confidence intervals give us a better clue as to what we can expect from individual elements taken at random from a population. Let me stop there. Okay, so if we go to the normal curve, if I were to say our data is going to fall right there on that green line, how sure would you be that if you were to pick something out of a population that it would fall onto that line right there? How confident could you be? So you think like 99% confident? I can say with 99% confidence, if I redid my test of events, asking the same questions over and over again, that our data that we would have picked would have fallen right there. So this has to be a very small confidence interval. We could say probably on that kind of scenario, we are 10% confident that if we redid our test, it would fall, our data that we picked, or our next piece of the information we picked, fall there. But if I were to say, take this, this could be a larger, we're more confident that if we were to pick a piece of data, it would fall within that region. So the smaller it is, the closer to 0 it gets. The bigger our area, the closer to 100% that we're going to get. Now, we're never going to get to 0%. We're never going to get to 100%, but we can approach them. Okay? And it all has to do with, when we started talking about normal curves, we had, within one standard deviation of a normal curve, you had 68% of the population. So the confidence interval there is, you can say, I'm 68% sure that if we reduplicated our events, that we would find our information there. If I go out a second standard deviation, you get to 95%, which would be where the 95% confidence would be. You go out one more, you get to 99.7% confident. So it has to do with on the standard deviation. So it has to do. And are we applauding for the right reason?
Hell yeah.
Hell yeah! Woo! Attaboy. Love it. So.
How'd you ask?
What? No, it didn't. What? No, it didn't happen. What are you guys talking about?
Oh, it didn't happen yet?
It's happening fifth.
Damn it, Logan!
Logan spilled the beans.
No. You got it. Thanks, dude.
How are you asking?
All right, Logan.
Tie-dye t-shirts?
Dude, we want to call launch.
No.
This is stuck
It's
up.
not happening.
We're stuck up.
What?
We're stuck up, man.
Nothing's stuck up.
Wait, are people gonna wear this? Yes.
Oh, I love it. Okay, shh, it's a secret. Sorry. It's
I don't
Logan's
even know
fault.
the girl. No one knows who the girl is. Who's the girl?
Who are you?
Tell me about it.
That's what I thought.
Dude, we're excited for you.
Thank you.
Logan said you were late because that was taking place
No,
now.
was
And I said,
talking
where is it happening?
Logan doesn't know who this is.
You had a bunch of shirts with letters on it.
I was dropping off props for my show.
I understand. I'm excited for you. Remind me to unmark you from being absent.
Okay.
Thanks. All right, so we're talking about the confidence interval. So here's the scenario they're going to give. And it's not the best scenario, but, again, let's just go with it. I think, again, we'll backfill some of the problems we had. Suppose we live in a remote scientific research outpost where electric generators only produce 90 volts. Okay, this doesn't mean anything to us, we're just telling us the story. The reason for the low voltage is the fact that the generators are old, inefficient, and too small for the number of people assigned to the station. Funding has been slashed, so new generators can't be purchased. There are too many people and not enough energy. Okay? So I will tell you that this scenario is actually why most homes in Arizona have swimming pools, especially if they were built in the early 70s to early 80s. They didn't have enough electricity on the power grid when it reached the extreme temperatures, and so you had something called a brownout that would take place. So you got only about half the electricity sent to your house during the hottest part of the day, which meant your air conditioning unit could not run. You had enough energy to run your refrigerator and maybe a fan or two in your house, but that was about it. So Suburban Project, who was the electric company in Arizona and still is, subsidized swimming pools for people to get. So when my parents put a swimming pool in 1975, it cost my parents about $600 to put a swimming pool in. Okay, it was a dug-in swimming pool, filter and everything like that. Salt River Project actually subsidized about $2,000 of the pool, meaning, oh, you want a swimming pool? We'll pay for the first $2,000. You pay for the rest. So you had some people that were actually, a $2,000 pool would probably get you a 5-foot deep end pool. We had a 9-foot deep end pool, so it cost my parents about $600 more. So that's kind of a different scenario, but it goes along with this electric generators thing. We find it necessary to keep the compound well lit at night, regardless, whatever other sacrifices we have to make. Okay, so this goes into your refrigerator worked during the brownout, but your air conditioning didn't because one's off of 110, one's off of 220. So we need bright light bulbs. We have obtained data sheets for a 550-watt sodium vapor lamp designed for 120-volt circuits, and these sheets tell us how much current we can be expected the lamps to draw in various voltage. Suppose we have obtained in the graph, so we have a good idea of how much current each bulb will draw from the generators that produce 90 volts. Estimate is mu, or the mean. So an estimated mean is 3,600 amperes, which there are some bulbs that will draw a little bit more than 3,600 amperes, and there are some that draw a little bit less. A tiny proportion of the bulbs draw a lot more or less than the average. We pick a bulb at random, which is usually what happens when anybody buys a single item from a large inventory. How confident are we that the current our lamp draws will be within the certain range of the size of the amperes? Okay, so it's kind of a, as I said, kind of a cruddy example, but you can think about this. If you knew, so let's put it in a little bit better perspective. Let's say you had a lamp you were replacing the light bulb in, and your particular lamp was supposed to take a certain amount of wattage for a bulb. So let's say your bulb that you're allowed to put in is up to 25 watts. So you go buy a light bulb from the store that says 25 watts. Theoretically, that light bulb should draw right around 25 watts. It might be a little bit more, it might be a little bit less, but it's not going to be exact. That's what they're talking about. So there's wiggle room or a fudge factor or however you want to, compress this information. So then it talks about the 68% confidence interval. Okay? So as imaginary data tells us the standard deviation and the distribution of amperes. According to the empirical rule, which we learned in a few chapters back, 68% of all elements in a sample have a parameter that falls within one standard deviation. So it's either to the right of our average or to the left. We don't know the actual standard deviation or the actual mean for the lamps of the situation, but we have an estimate. Okay, so again, talking about that light bulb. I'm putting a 25-watt light bulb in there. The circuit says it's going to hold 25, up to 25. The manufacturer realizes not all light bulbs will be the same. It might go all the way up to 27, might go down to 23, might even go further than that. So if you put something in there that is going to draw more current through the wire itself, it's going to blow the circuit. So if in that 25 watt you go and put a 300 watt bulb, it's going to create a large amount of heat in your system, and it'll eventually blow your system of your light bulb. Okay, then the 95% confidence works the same way within 2 standard deviation, and then the 99.7 works even further. So again, we're trying to figure out what our chance that we're going to pick something. Hey, that's kind of cool. That happened. We're trying to figure out what can, how confident are we that we're here or with the whole on this problem. So I want to walk through these problems a little bit and see how we do with them. And again, I only asked you to try them. You didn't have to master them, okay, because it's a little bit different than what you've been working with in the past. And sometimes it's a little harder to grasp onto. So 7.1. Okay, so 7.1 worksheet that I asked you to try. Number 1 says, in Roosevelt National Forest, the rangers took random samples of live aspen trees and measured the base circumference of each tree. It is known that the standard deviation for the circumference is this. Okay, so, and then it says the first sample had 30 trees. So you're going to conduct one thing. So you have 30 trees that you're talking about. Okay, the mean circumference, so the average of these trees has a circumference of this. And then we want to find a 95% confidence interval for the 30 trees. Okay? So you're going to go back and you're going to use this equation over and over. So you have E is equal to Z times that. Okay? So that's the equation we're going to go to for this problem. So they want us to find a 95% confidence. So what number do we use for 95% confidence? 1.96. Because it's 95% confident, that means I'm going to use 1.96. That's our z-score. Remember, our z-score is like our standard deviation. Okay? And then we're going to say, all right, we know that we have this as our standard deviation from our whole population of trees. We have much data, and now we're going back and analyzing 30 trees. So we know that's 4.63, and then we're going to do it over the square root of the number of trees that we're talking about. So in this case, over the square root of 30. So if you did this math on your calculator, this is going to come out to 1.657. And what makes this a 95% confidence interval is this 1.96 is the number we're using. So from there, we are going to do this. I'm going to do 15.71 minus 1.657. That's going to be our lower limit of our confidence interval. And then I'm also going to do 15.71 plus 1.657. And that'll give us our range with 95% confidence. So in this case, we're going to come out with this being 14.053 and 17.37. So what this means is, if I were to go out and reduplicate how I selected, think about your most vast forest we have here. Okay, we have some beautiful forests. Now, right around Winter Park, you've got those pine beetles that are doing a number. But there's some other forests you don't really have the pine beetles in that have different trees. So if I were to say, okay, how am I going to select these trees? There's some sort of randomized situation that's going to take place. If I go out again and select another 30 trees from the same forest, and I use the same randomization that I had done before, I didn't wait like 10 years later. I just I went out to look at these 30 trees. If I go out back one more time with 95% confidence, so I'm like at a really strong A, confident that if I did the same thing again, my range of my tree's circumference will fall between those two boundaries. Does that make sense? Kinda. All right, so if I take this a little bit further, so the next one says the next sample had 90 trees, okay, and you had the same mean, and again, we're going to try and find the 95% confidence interval. So now you are going to sample 90 trees. Okay? So this is going to be the same because we're still going to use the 95% confidence. The 4.63 is still the same. But what's my square root going to be? It's going to be 90. So is this a larger number in the denominator right now than it had been? Yeah, so if you go and you do the math, this is going to come out to 0.957, which means I'm going to do 15.71 minus 0.957 and 15.71 plus 0.957. And I'm going to find that this goes to 14.753 inches to 16.17. So this region, the distance between here, is a larger amount than here. Why? I'm sampling more things. So the more I'm trying to take at a time, the less confident, or the smaller my region is going to be that I'm not confident. Okay? 90 trees is triple the amount. 90 trees is triple the amount. But this region here is not, this is not triple the size of this. Okay? So the more and more you start taking, the more and more confident you can be with your 95% region, and you're talking about a smaller area, meaning this is a good thing. Okay? If I were to take this to 10,000 trees, this even gets smaller. If I take it out to 100,000 trees, it gets really small because I'm taking more and more data to satisfy what I already think should be true. Okay? So if this came out to 1 tree, this is pretty wide as far as the area, and it all has to do with the area underneath the normal curve. Okay? So on this particular problem, I might have felt this region was good. But because I selected more, I then get a larger area that I feel confident that my data is going to fall within. As I continue to grow this number, this continues to grow further and further and further out. Or, take it back. This could the bigger this gets, the smaller this gets. So, okay? So it's kind of like when you start looking at a pattern of events. Okay? Your friend has a coin, flips it, gets heads. How confident are you that the next throw is going to be heads? I don't know, 50-50. But if your friend tells you, hey, this coin, it's weighted awkward on one side, so one side is more likely to show up than the other side. Okay, so you already know that you have a bad coin. If your friend goes and flips it 5 times, and you get 3 heads and 2 tails, that's probably not enough information for you to say, yeah, that's a bad coin. Even if your friend throws it 5 times and gets all heads, it's still not enough information for you to make that justification. You have to realize that event has to take place a number amount of times, and you're going to start getting more and more confident that it's a bad coin by the number of throws that's taken place. In Vegas, the game of craps, which is played with dice, and each individual die is supposed to be weighted identical, and every now and then you'll get somebody that's going to sneak a loaded die onto the table, meaning it's going to have a heavier weight on one side. It has a heavier weight on one side. That side is more likely to be on the bottom. And if you were to do things like that, obviously it's very illegal, but if the casino's sitting there watching the die over and over and over again going, wow, there's been 3,000 throws of those pair of dice, and a 7 hasn't come out yet, the casino is going to think something's going on weird. Okay? if you put loaded die down on the table, and let's say the loaded die is set up to throw a 5 every time, if you throw that die once and you get a 5, does the casino think much of it? No. If you throw it again and again, and you throw it 10 times, you get a 5, 10 times in a row. Casino might be like, oh, it's kind of weird. What's the casino watching for? They're watching for, if you're just betting like a buck each time, and you're winning a buck back, casino's not going to lose sleep over it. But if you're like, okay, I'm going to bet $1 million if 5 comes up again, and all of a sudden, comes up again, casino's going to start looking at that person. Now, are they going to look at that person on the one-time bet? Guy walks up, $1 million, 5 comes up, roll the dice, walks out. Like, oh, just gave $1 million out. I actually gave $1.7 million out to that guy. So, something that Facebook uses as their technology and some of the other photography things is that facial recognition stuff. They're going to Facebook and it's like, do you want to tag, Chris Stirrup? You're like, dude, that is Chris Stirrup. That's me. How does it know it's me? It's using the facial recognition. It's the ratio between your eyes, your nose, and your mouth. And everyone's a little bit different. And Facebook uses it. But the casino started out with it. And I think I told you that the casino started out with the facial recognition stuff, not to recognize the cheaters, but they were recognizing the whales. And the whales are the people who are the high-end gamblers because they knew that if that person comes in and they have a $2 million marker at any given time in the casino, meaning that's how much the casino as the person is going to bet. If our facial recognition recognizes this guy coming through the front door, we're going to make sure that the appropriate people are surrounding this person, giving them, hey, we have show tickets, we have front row for tonight's show, in the MGM Grand, arena, wherever this person is. Oh, well, thanks so much. Oh, we have your favorite table at the steakhouse. Reservation for 6 or 6:30 did you want? 6:30, fantastic. So that's why the casinos came up with the facial recognition program, and then they realized, hey, wait, people who are cheating should also be part of this facial recognition program so we can make sure that they don't come back by our casinos. Okay? So if I continue one more slide, we are then going to get to 300 trees. So our first situation, we were this confident, took some more trees, we became this confident. Now I'm taking 300 trees. So what can you tell me with our colors? Will we be outside of the black with 300 trees? Will we be to the right or the left side of the black with 300 trees with our confidence interval? Or will we be inside the red? Why are we becoming more confident that our information is going to fall there? Because again, this 300, we're going to put it here. This 300, if I put it there, gets to 0.524, which means you're going to go 15.71 minus this, and 15.71 plus this. So my confidence interval is getting even smaller because I've taken more. So I have 15.186, 16.23. Okay? Did I do that math right? I think I did. So we're even closer together here. We're more confident because we took more. Okay? What do you notice with the intervals as n increases? The interval, the confidence interval shrinks as I start taking more and more and more. Okay? If I had 1 million objects out there and I test all 1 million, and then you have that million sitting there, how confident would you be that you fell between these two regions? You'd be really confident that it fell into this really small region. Okay? Problem number 2 talks about Forbes. This is a magazine. Gave data about a percentage of return on capital for 41 representative stocks in the entertainment/information sector. Stocks such as CBS, Turner Broadcasting, Walt Disney, Time Warner, Gannett, and so on were included. It is known that the standard deviation is 0.73, or 7.3, excuse me. So that's our standard deviation. The sample is 41 stocks. Okay, we're looking at 41 different stocks, and we have an average of 11, or a mean, or an average of 11.57% return. Does anybody know what an 11% return, how long does it take to double? Somebody with a calculator? So you have to do it real quick. Katie, get a calculator. Ready? 72 divided by 11.57. Means that if you have 11.57%, 6.22 years would take to double your money. It's called the rule of 72. I don't know if you knew that, but it's whatever percent rate that you have. It's called the rule of 72. So the 72 divided by whatever that percent is, and it'll let you know. Don't turn your percent into a true decimal. Okay, find an 80% confidence interval. Okay, an 80% confident interval. 80%. So, 80%. Do we have 80% written on our back pages? Now we have 90, 95, and 99.
1.282.
How much?
1.282.
How you got that? Yeah, I think you're right.
No, yeah. So you put the 10% on each side.
So, you're talking about 80% of the area here, yes? That means 10% here and 10% here. So on your calculator, if you do the inverse norm
0.1.
of 0.1, good. So I'm going to go second, bars, inverse norm, and I'm going to do 0.1. Now, if you're yours is going down the screen, make sure it has your average of 0, your standard deviation of 1, I think it is. So if I just do the inverse norm of this, it's going to give me negative 1.28, and we're going to keep that positive. So I'm going to take that, and I'm going to know my confidence interval. I'm going to go with 1.28. I'm going to keep it positive. Okay, I'm not worried about a negative area, and that is my standard deviation that I'm going to deal with. Okay?
Wait, you keep what, 0? When you invert or something?
Is yours going down the screen?
Yeah.
Okay. So whatever your initial setup would be. Okay. That should be fine. Okay. Yeah, there it is.
Oh, okay. Thank you.
Why do you do that?
I'm sorry, what?
Why do you do that?
Okay, so I know that if I'm talking about an 80% confidence interval, I'm talking about 80% of the area is on the normal curve. So over here we have 10% of the area, and over here I have 10% of the area. Remember, the normal curve always finds the area that's to the left of the z-score. So we're looking for that. So it's 1.28 or negative 1.28 standard deviations. So if I go negative 1.2 standard deviations to the left, I'm talking about 10% of the area of the curve area. This is a lot to that. And you keep it positive because you're not worried about it being there. Okay. So, we have 41 stocks, so this is our N, and we're going to use this equation again. We're going to use E is equal to our observed Z, or standard deviation. Okay, so for Z, I'm going to plug 1.28 in. They tell us we have what did they tell us? Oh, I forgot to put that up there. We told us the standard deviation is 7.3 from our data. Oh, it's up on top, duh. So I'm going to go 7.3 over the square root of N. N is the number of stocks we're talking about. We're talking about 41 stocks. So if you go and you figure this out, this is going to give us 1.46. So then you're going to take your 11.57 and subtract 1.46. That'll be the lower portion. And you're going to go 11.57, and you're going to add this. Squeeze it out. And that's going to give you your 80% confidence interval. Okay? Are you really confident with an 80%? 80% confident. You could be like the weather guy. Could you imagine being the weatherman? Dave Aguilera lives down the road from us. And I always find it funny that he can have a job that made the wrong prediction on the weather. Or, what kind of job do you got? Hey, so I'm a weatherman. So you're not right. You often make mistakes in your job. It's like the only job that you can totally goof up and still have a job. Because then they go, no, well, this showed what our patterns were, but then it happened. It's supposed to be 102 degrees, but it snowed. And I suck. Every time I see Dave Aguilera, he's the nicest guy in the world. And you know what I always say to him when I see him? It's a nice day. Duh! He called the weather. He's a good guy, though. Real good guy. Okay. For problem number two, or B, they're talking about an 85% confidence interval. Okay? So on the page before, do I have an 85% confidence? No, I have 90, I have 95, and I have 99, right? 1.4? So if you have this, if you had 85% of the area here, then this area and this area are going to be 15%. So how big would one part of that area be? 7.5. Okay? So 7.5%. So if you use your calculator, you do your inverse norm. So you do 0.075. So second bars, inverse norm. If I move the decimal twice left, I get 0.075. Close the parentheses, or make sure your mean and your standard deviation, mean is 0, standard deviation 1. You do this. This gives us negative 1.44 roughly. So negative 1.44, I'm going to keep it as positive 1.44. So this is my new Z value. So what's changing up here? What changed on this problem? What part of this problem right here is going to change? What am I replacing 1.44 with? 1.28. So here, I'm going to plug in. So I'm going to go 1.44 times 7.3 over the root 41. And then that's going to give me 0.957. Wait. I looked at the wrong one. 1.64, thank you. Which means I'm going to change this and this. So I get 11.57 minus 1.64, comma 11.57 plus 1.64. Okay? So, are you talking a smaller area? Yeah.
I have a question.
Uh-huh.
So you've got the 1.64 and then the other one, the 1.46, by solving the 1.287. That.
I did the inverse norm
Of that.
of whatever the area to the left of my furthest standard deviation. So I'm finding the area of that.
Okay.
How many standard deviations would that be? It'd be that 1.28 standard deviations that way to incorporate 10% of the area under the curve there. This one being at 7.5% of the area, so I'm looking for that area, inverse norm. So it's 1.44 standard deviations that way of the average of the normals.
So you times that.
Yep. And then last one, then it asks for the 95% confidence interval. And the 95% confidence interval that's one of the given scores. 95% interval. Oh, I just looked at it and I forgot. 1.96. So then I'm going to change this to 1.96 times 7.3 over the square root of 41. And so that's going to come out to 2.23. So 11.57 minus that, and 11.57 plus that. So as the confidence interval gets closer to 100%, the wider you have to be in order for your confidence interval to take place. Okay? So, guys and girls, I think I have left you with enough information that you will be able to do problem number 3, 4, and 5. Sound good? Sound good?
That's how much, right?
Yeah, 3, 4, and 5 on 7.1. I was supposed to go to 7.2, but I don't have the heart to make that move yet. Sorry. Sound good? All right. Good job today, guys.